I always find these large areas of sky rather difficult. There's no real pattern and very little variation in colour, so there's not much to go on. For instance, I thought that this piece might fit here, but I soon found out my mistake, because when I try it, it just won't fit. It may often look as if two pieces are the same, but in fact, the shapes never repeat themselves exactly. Well, that's just what makes jigsaw puzzles so interesting. But what has all this got to do with the kind of periodic patterns that we are studying in our course?
Well, of course, a completed jigsaw puzzle is a tiling, of part of the plane at least. And it's not difficult to see that jigsaw pieces could be all of exactly the same shape. This shape, for example. What I'm claiming is this, that if I take lots of copies of this shape, then I can cover as much of the plane as I like with them. Now, is that true? Well, now, if I simply try to fit two pieces together the same way up, then there's no way that they fit. But there is a way to fit them. If I turn one of the pieces upside down by rotating it through 180 degrees, then they do fit together. And look, I can completely surround my first piece with rotated pieces. Well, now, what about these gaps on the diagonals? Can I fit pieces in there? Let's start here. Each of these two pieces is upside down relative to the first piece. So that means that a piece that's the same way up relative to the first piece will fit both of them. And so it does. And in exactly the same way, I can fit a piece into each of the other diagonal gaps. There we are. Now there's nothing to stop me. I could go on fitting more and more pieces around these and fill the entire plane with identical copies of these pieces, just by following the single rule that when two pieces are fitted together, they must be opposite ways up. The vital point to realize is that the rule which says how pieces are fitted around a particular piece works also for every other piece. In other words, if you imagine yourself standing on a piece, the pattern as a whole will look exactly the same no matter which piece you've chosen to stand on.
Now that's beginning to sound more like mathematics, isn't it? Can you recognize the mathematical property of the pattern that corresponds to this fact? If you need more time to think, pause the tape. Well, the answer is the symmetry group of the pattern acts transitively on these jigsaw pieces regarded as tiles in a tiling. There is always a symmetry which will map any chosen tile to any other tile. We call this a transitive tiling, as you've seen in the text of the unit. Now let's look at a different example. Suppose all of your pieces were of this shape. It looks much simpler than the last one, but when I try it, it doesn't seem to fit. Suppose I allow myself to turn some of the pieces over and use them back to front. Now, of course, I wouldn't be allowed to do this with ordinary jigsaw pieces because they have the picture only on one side. But the back-to-front shape is just the reflection in the two-dimensional plane of the original shape. And we certainly allow reflections in the symmetry groups we are studying in M336. So do you think that you could tile the plane with just this one piece, allowing some copies to be reflected? To help you, we've reproduced the shape and its reflection in the video notes. Well, the way it's done is this. To fit a piece immediately below the original, it has to be reflected in a vertical axis. And the same is true of the piece immediately above. So what of the pieces either side? Well, they too have to be reflected, but this time in a horizontal axis. And so the rule that defines the pattern is this. For two pieces to fit, one of them must be reflected about the axis joining their centres. Now, what does this imply for the pieces that touch the centrepiece diagonally? How do they fit in? Well, in fact, they have to be rotated through 180 degrees. And the reason it's a 180-degree rotation is because it's the composite of two reflections in axes at right angles to each other. So we now have a consistent scheme which you can keep going indefinitely. To fit a piece vertically, you reflect in a vertical axis, and to fit a piece horizontally, you reflect in a horizontal axis.
Now, where's all this heading? Well, you've seen two different rules for fitting jigsaw pieces together to tile the plane transitively. The first example involved rotations only, whereas the second required reflections as well. The exact details depend on the shape and on how the copies fit together in the pattern. So the rule for how pieces fit round a particular piece is a distinctive feature of the pattern that we can use in classifying tilings into different types. And this is what we're really looking for, a sensible classification into different types. But before we go into the details, let's look at a more interesting shape. Look at this chap. Could we make a jigsaw out of copies of him? Or in other words, can we tile the plane with him? Well then, let's have a go. I think you can see that the hook for the nose and mouth can only fit with an upside-down copy of itself. There we are. And now, the smooth curve of the neck looks as though it should fit with the smooth curve of the back of the head. Yes, and if that works, it means that this back of the head here should also fit in with the neck. And so it does. Now, how about the top of the head? Well, the bump on the top of the head fits in with the bump of the brow, I think. Yes, and that means, finally, that this brow should fit in with the top of the head of another copy. And so it does. And there we are. I've surrounded the original piece with 5 copies. And I could carry on indefinitely to tile the plane. That's because this is another transitive tiling. But now let me try to find a notation for keeping track of how these copies fit together. We found that the perimeter of the cartoon man is divided into 5 segments, each of which fits onto a rotated copy of itself or of some other segment. So we can put 5 vertices on his perimeter, dividing the segments from each other. And we can label the segments going clockwise A, B, C, D, E. And we can label the segments of the surrounding pieces in exactly the same way. Now, if we concentrate only on the labels which are adjacent to the centerpiece, we can now describe how the pieces fit together. Segment A, the nose and mouth, fits onto segment A of an upside-down copy. Segment B, the neck, fits onto segment C, the back of the head of another copy, and vice versa. Segment C fits onto segment B of another copy. Then segment D, the top of the head, fits onto segment E, the brow of another copy, and vice versa. E fits onto D. We can record this with 2 rows of symbols. The top row representing the piece we're surrounding, let's call it the reference piece, and the bottom row records the corresponding segments of the adjacent pieces. The complete block of 2 rows is a simplified version of what the unit calls an incidence symbol. This 2-row symbol describes how the pieces fit together. Later on, we'll be able to use this scheme to help classify transitive tilings. But there are other ideas which we must develop before we can do that. Remember, in the text of this unit, you've seen that there are only 11 possible tile types for transitive tilings, namely the 11 Larvies tile types that you met in the first unit of the course. In other words, if we go round a tile, looking at how many tiles meet at each of its vertices, we get just one of the 11 types listed here. Now, which type is this? Let's add a couple more pieces to help you. Then you should be able to work it out. The tiling's reproduced in your video notes. The answer is 33434. There are 3 tiles surrounding this vertex, 3 surrounding this vertex, but now 4 tiles surround this vertex. Then 3 surround this one, and 4 surround the final vertex. So our tiling should be an elastically distorted version of the Larvi's tiling 33434. And so it is. You can see we're getting there. If you're interested, you could try doing this sort of thing yourself. If you use one of the transitive tiling pictures in your tiling envelope to fix the vertices, then you can develop your own wavy edges, as long as you do it consistently. Now, this kind of elastic distortion doesn't change the adjacency type of the tiling, but it can change its symmetry properties. The Larvi's tiling 33434 certainly has reflection symmetries, but our cartoon tiling doesn't.
What we want is a classification scheme for transitive tilings which seems intuitively right. To achieve this, we must obviously include the symmetry information as well as information about the Larva's type. After all, we've just seen that tilings of different symmetry types do look quite different, and so intuitively we want to regard them as different. On the other hand, there are some physically different tilings that we might feel intuitively should be in the same class. For example, if you apply the kind of deformation that Fred recommended you to try, this allows you infinitely many possibilities. But we wish to classify all transitive tilings into a finite number of classes. What we shall do is to say that 2 transitive tilings are in different classes if, firstly, the adjacency types differ, or, secondly, the symmetry groups differ, or, thirdly, even though their symmetry groups are the same, they act differently on the 2 tilings. This third kind of difference may sound rather abstruse, but actually it's quite easy to detect visually. So let's see examples of all 3 kinds of distinction between transitive tilings. These 2 tilings have different adjacency types, but the same symmetry group. Each has rotation centers of order 3 and of order 6. The tiling on the left has a rotation center of order 3 at the center of each tile, and a rotation center of order 6 at each vertex. But it's the other way round for the tiling on the right. The rotation centers of order 3 are at the vertices, while those of order 6 are at the centers of the tiles. In contrast, these 3 tilings all have the same adjacency type, 4, 4, 4, 4. But clearly, they have different symmetry groups. The first tiling has rotational symmetries of order 4. The second has only rotations of order 2. It does still, however, have reflection symmetries, but the parallelogram tiling doesn't even have those, because if you reflect rightwards leaning parallelograms, they become leftwards leaning. But now take a look at this pair of tilings. They're both of the same adjacency type. It's 4, 4, 4, 4 again. And they even have the same symmetry group. It consists of translations in 2 directions, 180-degree rotations, and reflections in vertical axes. But in the first case, these vertical axes go through the centers of the tiles. And in the second case, they go between tiles. What we're really seeing in each case is the symmetry group of the wavy lines. The vertical dividing lines between the tiles are in different positions in the 2 cases. Consequently, although the symmetry group is the same in each case, its action is different. In the first case, the stabilizer of a tile includes a reflection. In the second case, it doesn't. Well, now, that's really thrown up quite a challenge. We're saying that we want to take account of all those subtle differences in the action of the symmetry group and produce a classification that's reasonably easy to use. Is it possible? Well, yes, it is. In the late 70s, Branko Grunbaum and Geoffrey Shepard succeeded in finding all possible symmetry group actions on transitive tilings. And they proved they'd listed them all. The way in which they accomplished this remarkable feat relied on incidence symbols. It turns out that the incidence symbol, together with the adjacency type, completely determines the way the symmetry group must act on the tiling, and vice versa.
We've already constructed a simplified incidence symbol for our cartoon jigsaw tiling. If we do the same for our first jigsaw tiling, we can then move towards a more rigorous definition of incidence symbol. The perimeter of each piece has 4 segments. In fact, its adjacency type is 4, 4, 4, 4. We'll label the vertices of the reference piece A to D, and the edges little a to little d. Now, how about the incidence symbol? Remember how we fitted this puzzle together by rotating each adjacent piece by 180 degrees. So, see if you can complete the incidence symbol. The answer for the second row is again A, B, C, D. But now have a look at this. The left and right sides of this piece are the same as for our first puzzle, but the top and bottom sides are different. I can build up a horizontal strip of this jigsaw the same way as before, by rotating alternate pieces 180 degrees. But now, the pieces above and below don't need to be rotated, or reflected for that matter. They can be in just the same orientations. And that means that for vertical strips, all the pieces have to be the same orientation. So that tells us about the diagonal pieces. There, here again, there, and there. So, what will the incidence symbol be this time? Well, first of all, you have to choose how to label the edges. Let's start with letter A on the right. The answer for the second row is A, D, C, B. So A and C are repeated in the same position as in the first row, but B and D are interchanged. But this isn't the only way of consistently arranging these pieces. The pieces either side of the center one do have to be rotated right enough. But the piece below doesn't have to be in the same orientation. I could choose to flip it over about a vertical axis. And of course this would make all the pieces in this row flip over. And I can extend this into a transitive pattern by flipping over alternate rows. That means flipping over the top row in this case. When I do that, the rule around any one piece works for every other piece. It's a different rule from the one that doesn't involve flipping, and that's reflected in the fact that we've now got a different symmetry group acting on the pattern. What's the incidence symbol this time? The answer for the second row is A, D, C, B. Once again, A and C are in their original positions, and B and D are interchanged. Oh dear, the rule for how the pieces fit together is different, but it seems to give the same incidence symbol as the original pattern. So our symbols aren't always distinguishing between different possibilities. Let's see what we can do about it.
If we want to be able to distinguish between these two patterns, we have to be a bit more subtle. We have to take account of the direction of each edge. Let's start with the original pattern, and let's take the reference piece and work our way around the inside of its perimeter in a clockwise direction. The arrow on each edge now indicates the orientation we have given that edge. Let's now transfer this information to the incidence symbol. We attach an arrow above each letter to indicate the orientation of the corresponding edge. Now what about the bottom row, corresponding to the 4 pieces adjacent to the reference piece? Well, we have to label these adjacent pieces exactly like the reference piece, including the newly attached arrows in the correct directions. Remember that this arrangement of pieces is the one where the pieces above and below the reference piece are just translated copies of it. And the pieces to the left and right are rotated through 180 degrees. In order to transfer the attached arrows to the instance symbol, we have to look at each edge of the reference piece and compare the direction of arrows either side of the edge. For the first edge, the arrow in the adjacent piece points in the opposite direction to that in the reference piece. And so we make it point in the opposite direction in the incidence symbol, from right to left. For the next edge, the 2 arrows again point in opposite directions. And so the arrow in the incidence symbol must be opposite to the one above it. And the same is true for the last 2 arrows in the incidence symbol. Let's keep a record of this and then turn our attention to the alternative arrangement of jigsaw pieces, with the pieces above and below the reference piece reflected in a vertical axis. The consequence of this is that the A, B, C, D go anti-clockwise in the reflected pieces, with the arrows pointing anti-clockwise too. And of course, this will make a difference to the incidence symbol. Look at the 4th letter in the bottom row, B. This must now get an arrow that's in the same direction as that of the reference label D. Likewise, the 2nd label in the bottom row must also have an arrow in the same direction as the reference label above it. For the symbols in the 1st and 3rd positions, the arrows must still point in the opposite direction to those of the reference labels. With that, we've achieved our goal. With the arrows added, the incidence symbol now gives us a complete record of the way in which the pieces are fitted together. When the rule for fitting the jigsaw together is altered, so also is the action of the symmetry group. And that is precisely recorded by the changed incidence symbol.
So it seems that we can now classify a transitive arrangement of pieces or tiles by noting just 2 things about the arrangement. First, the adjacency type. This tells us which of the Larvi's tilings it can be obtained from. Our 3 jigsaw puzzles were all of adjacency type 4444, while our cartoon tiling was 33434. And the second thing we have to note is the incidence symbol. This shows us both the segments of the tile perimeter which fit onto each other and the directions in which they fit. If you want to check that you really understand what we're talking about here, see if you can apply the ideas to our first jigsaw puzzle and also to the cartoon character tiling. Try to work out the incidence symbols for these 2 tilings. You've already seen where the letters go. All you have to do is to get the arrows right. The pictures are repeated in the video notes. The pieces of the first jigsaw puzzle were so designed that each edge segment fitted the same segment on the adjacent piece, but in the opposite direction. So the arrows in the incidence symbol must also be reversed, pointing right to left. And this also turns out to be the case for the cartoon tiling. The arrows in the bottom row are reversed.
So far, we haven't had to worry too much about symmetry because none of our jigsaw pieces themselves had any non-trivial symmetries. It's true that adjacency type and the incidence symbol completely determine the action of the symmetry group on the tiling. But nevertheless, we've never needed to think about symmetry in constructing these symbols. But it isn't always so simple. there are times when we do have to take symmetry into account in order to build up the incidence symbol. Just take a look at these. They're all identical, so let's see what can be done with them. Well, I can fit these two pieces together, and if I rotate this one, they still fit. Of course, it all amounts to the same thing, because rotating one of these pieces actually makes no difference. The piece itself has 180-degree rotational symmetry, and you can't tell just by looking whether or not I had rotated a piece before fitting it. And so putting this jigsaw together should be fairly straightforward. I can go on adding more and more pieces. But now you see something rather strange, because although the pieces are 1, 2, 3, 4-sided, they don't fit together in a 4-4-4 manner. You see here we have 3, here we have 6, here we have 3, and here we have 6 again. And so the tile type is actually 3, 6, 3, 6. Now, how about the incidence symbol? We'll start by lettering the edges just as we did before. However, this time, when we've gone round 2 edges of the tile, A arrow, B arrow, the next edge we come to has precisely the same shape as the first. And so I'm going to label it A arrow again. And then I find that the 4th edge has precisely the same shape as the second. And so I shall use the same label, B arrow. Altogether then, I have the first row of the incidence symbol as A arrow, B arrow, A arrow, B arrow. Now, if you think I'm cheating by using each label twice like this, remember what I pointed out a couple of minutes ago. You can't tell the edges apart. There is no way of knowing whether or not a tile has been rotated before being fitted in. The tile has a center of rotational symmetry of order 2. In fact, it's a symmetry of the tiling as a whole. And the incidence symbol itself embodies this symmetry. You should now be able to complete the incidence symbol for yourself. Edges A and B actually fit one another when one is reversed in the adjacent tile. And so the second row of the incidence symbol is BA, BA, all with backwards arrows.
Now we want to be sure of covering all the things that you need to watch out for. And for that we need one last example. This tile type is one that you've already met earlier on. It's actually 33434. Now what about the incidence symbol? This time, for each tile, there's a reflection symmetry of the whole tiling that actually bisects an edge of that tile. Consequently, if we start at the straight edge of a tile, it's no longer appropriate to use A arrow because the 2 possible directions along the edge are indistinguishable owing to the symmetry. So we label the straight edge A without an arrow. But then the next 2 edges do have distinguishable directions, so we label them B arrow and C arrow. But now, the fact that there's a reflection symmetry down the middle of the tile means that the 4th edge is indistinguishable from the 3rd edge, except that if we keep going clockwise around the tile, we're traversing it in the opposite direction. And similarly, the 5th edge is the same as the 2nd, traversed in the opposite direction. So, in our incidence symbol, the top row is A, B arrow, C arrow, C backwards arrow, and B backwards arrow. We'll try working out the bottom row for yourself. The segment A fits onto itself, and since you can't tell the difference whichever direction it goes, the first symbol in the bottom row is just A again without an arrow. Segment B fits onto segment C, but whenever this happens, one of them has to be reversed before they can be fitted together. To record this fact, the bottom row has the arrows reversed relative to the top row.
Once you get the hang of them, incidence symbols aren't that difficult to construct, and yet they do convey a remarkable amount of information. As we've already said, by using incidence symbols in conjunction with the adjacency symbols giving the lavas types, we are able to give a complete classification of all possible transitive tilings. If two such tilings of the same adjacency type also have the same incidence symbol, then they can differ by at most an elastic deformation, and they will have the same symmetry group acting in the same way. And in 1977, Grunbaum and Shepard proved that the number of such distinct types is just 81.
Ah, yes, but did you know that in 3 dimensions it's infinity?